Before we start chapter 9, let's do the last example problem on chapter 8 notes. So this one, the last page. So conduct the appropriate hypothesis test. Now, a pharmaceutical company manufactures a 200 milligram pain reliever. The company's specifications require that the standard deviation of the amount of the active ingredient must not exceed 5 milligrams. The quality control manager selects a random sample of 30 tablets from a certain batch and finds that the sample standard deviation is 7.3 milligrams. Assume that the amount of the active ingredient is normally distributed. Determine whether the standard deviation of the amount of the active ingredient is greater than 5 milligrams or not. Okay, so the key word here is you want to claim that whether the active ingredient is greater than the 5 milligram or not. So the null hypothesis is the standard deviation is 5 milligram, right? And now the alternative hypothesis, you want to claim that whether this one is bigger than 5 milligram. So bigger than, this is the right tail, okay? And this one is all about the standard deviation. So we will do something with the chi-square testing, okay? And this one is already stated that we randomly selected. That means this is a normal distribution and simple random sample, okay? So those requirements are met. Now we need to find the chi-square. So find the best statistic. So chi-square, this one has n minus 1 over sigma naught square and multiply by s square here. Okay, and n here is the total number of the sample, in this case 30, right? So we have 30 minus 1. And how about the s and the sigma at the bottom here? Here the s squared is the sample standard deviation, and it is given at 7.3 milligram. So we have 7.3 square, and this one is the original or the null hypothesis, right? Or 5 milligram. So we have 5, right? This is the null hypothesis value. This is the sample that we are testing for, 7.3, and make sure this is square. So let's do the calculation and see what we get for here. So we have 30 minus 1, 29. 29 multiplied by 7.3 square and all the way divided by 25, and that's give me 61.8164. Don't forget that the degree of freedom is n minus 1. In this case, 30 minus 1, 29, and alpha in this case 0.05, right here, level of significance. Now after we get the test statistic, we need to also figure out the chi-square of alpha. Okay, so alpha is 0.05. So we're looking for chi-square of 0.05 when the degree of freedom is 29. So let's go back to the chi-square table. So 0.05 is right here, this column. and we have 29 degrees of freedom. So go down all the way here. 29 is this one, right? This one is 29. So 42.557. 42.557. Go back here. That's equal to 42.557. This is the critical value. Now you're gonna draw the right tail curve. So let me draw the right tail curve here. Okay. So we have this is all the way to the right. So this is chi-square alpha, and this happened to be 45.557. Okay, so it should be assume that we draw the correct one. Then from this point is 45.557. Now our test statistic is 61.81. So 61.81 is should be bigger than 45. So maybe around here, right? Around this point. This is the test statistic. And because the test statistic is in the region of the critical value, so if this one is inside the critical region, then we reject this. Okay, so we reject the hypothesis, the null hypothesis. That means our claim is correct. That means the active ingredient is bigger than or greater than 5 milligram. Okay, so that is the end of the last example. Now let's move on to the next chapter here. So this chapter, the next one for chapter 11 in our textbook, it should be chapter 9, and this section should be 9.2. So in the last two chapters 7 and 8, we talk about the population proportion, the mean, and standard deviation, also the hypothesis testing. Now in this chapter we will talk about the inference about the two population, meaning that we compare not just one population at a time, but we compare two of them at the same time. And we also consider the two population proportion, and then the mean, and also the standard deviation for the last case. So the first section, before we're doing anything, make sure that we will understand the difference between independent and dependent sampling. Now when the individuals selected for one sample do not dictate which individuals are to be in the second sample, that means they do not depend on each other, or in this case you have independent sampling. The second case, when the individuals selected to be in one sample are used to determine the individual in the next or the second sample. That means they do depend on each other, or we call it the dependent sampling. Dependent samples are often referred to as the matched pair samples, right? Where the pairs of data are matched together for comparison based on some characteristic. So if you do compare something against each other, that should be the dependent sampling. And it is also possible for an individual to be matched against him or herself. Okay, so try this case, the first case, and see if this is independent or dependent sampling. Researchers want to know whether the price for a one-night stay at a holiday express is less than the price of one-night stay at a red roof. Now they want to compare the price. So C randomly selects 8 towns where the location of the hotels is close to each other and determines the price of one night stay. So it is dependent or independent. This sampling method is actually dependent, since each of the Holiday Inn Express hotels can be matched with one of the Red Roof Inn hotels by town. The reason that this case is dependent, because let's say you select 8 towns, and let's say the first town, for example, town A. Okay, the first town is town A. So when I first select town A, I select one Holiday Express, and then the next hotel, make sure that I have to select the Red Roof, because they have to have 2 different hotels in order for me to compare that. So the second hotels will depend on the first hotel that I select and make sure that they are different, right? Because in the same town, if you want to compare, then in the same town, make sure the 2 locations are 2 different hotels, and one of them will depend on the other one. Once you select one, then you can decide the next one. So that means they depend on one another. Now consider the next case. A researcher wants to know whether the state quarters introduced in 1999 have a mean weight that is different from the traditional quarters. So they want to compare the weight of the quarters between the states and the traditional quarters. Now he randomly selects 18 state quarters and 16 traditional quarters and compare the mean weight of the sample. In this case, they are independent, because let's fill out this word first. So they are independent because the state quarters which was sampled had no bearing on which traditional quarters was sampled, right? You just take 18 randomly 18 state quarter, and then you can take another 16 traditional quarter, and once you have this one won't depend on what was state quarter that you chose. The last case for the hotels, because we choose 8 different towns, the first town, make sure that we have 2 different hotels, so that one has to depend on the other. But in this case, I just randomly select 18 states quarters, any places, and then the other one I choose another 16. They have no dependent on each other, right? Also notice that we are comparing the means to each other rather than a direct comparison of one quarter. So we do not compare one quarter to the one quarter, but we compare the means of all of them to the mean of the other label together. So that is the independent and dependent sampling. Let's move to the next objective. So we will also learn about the hypothesis test regarding the difference between the 2 population proportions. So this one is about the population proportion, but we are testing for the difference between 2 of them. The requirement for testing is that the 2 population proportion P1 and P2, they must have the following requirements. The samples are independent obtained using the simple random sample, right? This one we already know from last chapter, bigger than or equal to 10, and we have two proportions, so make sure you do P1 and P2, right? and then each sample size no more than 5% of the population size, and usually this one is met. And we call the poor estimate of the proportion is given by p hat x1 plus x2 over n1 plus n2, and you will see how this formula is applied soon in the next example. Now, there are some steps in hypothesis testing. The first thing is you have to determine the nose and the alternative hypothesis. And again, they still have three cases: the two tails, left tail, and the right tail. So now, the null hypothesis, they are all always equal to each other. So the first proportion and the second proportion, they are all equal to each other. This is the default case. Now, we claim that for the two tails, they are different. For the left tail, the first population is less than the second one. The right tail, the first one is bigger than the second one. But the null hypothesis, they are all equal, and this is the claim or the alternative hypothesis. Again, you have to select the level of significant level or alpha, and this one is usually given from the problem. And you have to calculate the test statistic, and we do a z score for proportion, right? Remember, for proportion we do z score. For the mean we do the test the student t distribution, and for the standard deviation we do the chi-square. So the test statistic, we take the p hat 1 minus p2 over p 1 minus p, and here p is follow this formula, and 1 over n1 and 2, right? And after we have that, we're gonna find the p-value and compare that. So if your p-value is less than the alpha level, then you reject. That means your p-value is really small. We should reject that. Okay, so that's basically the same rule comparing to the last chapter, but in this case we include two samples. So the first example is the testing of the hypothesis regarding the two independent population proportions. An economist believes that the percentage of urban households with the internet access is greater than the percentage of the rural households with the internet access. So from this one, the keyword is greater than here. Greater than, that means the urban is bigger than the rural. Okay, or we can call this is the first one, this is the second one, just to label them. Okay, we're using 1 and 2, so I call the urban to be 1, the rural to be 2. So they believe, that means they claim, right? So this is the alternative hypothesis, the claim, versus the null hypothesis, which is originally they should be equal, right? So from the last here, originally they should be equal to all of them. Now they claim that the first one here is bigger than the second one. So this is the right tail. Now after they make the claim, he obtains a random sample of 800 urban households. So this one, 800, is the sample, the number of sample, or n1. And they find that 3 of them have internet access. That means out of the total sample, we have this is the x1. So x1 here is where we talk in above here, x1. So x1 is a value that we found from the collection. And then we also collect 750 rural households, or this is the N2, the total number of sample, and we find that this number, or x2, we have this internet access. Now alpha is 0.05. Okay, so let's see if we reject this claim or we accept that. So the requirements, you have to make sure that this one is bigger than 10. So N1, which is 800. P1 is what? P1, remember, P has x1 plus x2, N1 plus N2. But P1, P has 1 is the individual for the number 1, or P has 1 is equal to x1 over N1, or 338. This is just a proportion over N1 is 800 right here. So we got that here, and 1 minus P has 1, and this one is bigger than 10. I do the same testing to the second sample, and it is also bigger than 10, so we are good. So we can assume that they are normally distributed. Okay, so now after we have everything, we can do the hypothesis testing setup. So the null hypothesis, they are always equal, right? And now we claim that P1 is bigger than P2, because rather than here. So this is the right tail, right? The right tail. Or if you want to move P2 to the left side, you can also subtract that, and you have 0 on the right side. Or you have P1 minus P2 bigger than 0. There are two ways you can write that. I prefer the first one, because we follow what we had above. The level of significance is 0.05. So now let's do the test statistic. So we know how to calculate P1, P2, right? P1 is just P1 has it's just x1 over N1, and x1 is what, 338 over 800. The same thing to P hat 2 is x2 over N2. x2 is 292 over 750. And then remember P hat, this is the combine of 1 and 2, so I use this formula. And we already have all the info. x1 here, x2 here, and 1 and 2 is here and here. So that's good. So when you plug into the z statistic, or the test statistic here, so this should be 0.422593, and this one is what, x1 338 plus x2 292 over, and you should guess 0.4065. Now I just plug in directly P1, P2, and then P 1 minus P over just everything we already have. So here becomes 0.425 minus 0.3893 over P has here 0.4065, 1 minus that, and then another square 1 over n1, 1 over n2. And if you do the correct calculation, you should get 1.33. Now, once you get the test statistic, you need to find a p-value using the normal CDF. Now this is the right tail, right? So let's draw the curve first. This is the z. This is 0, right? We have 1.33, so it should be around here. And then this is the right tail, so from this point and all the way to the right. Right. So the p-value using TI 83 or 84, you use the command the command of normal CDF, and then the first input should be 1.33. The second one is all the way to the right, so I use 10 to the power of 99, right? It's extremely large number to the right. And if you do that correctly, you should get 0.0918. And this one is, in fact, it's bigger than the 0.05 or the alpha. So because this one is bigger than, we do not reject. If we do not reject, that means there is insufficient data or evidence to conclude that the percentage of urban households with the internet access is greater than. So the claim is not good. Right. Okay, so let's move to the next example. This one, we also construct and interpret the confidence intervals for the difference between the two population proportions. Okay, so here we will talk about more about the confidence interval. So we come back to the concept we learned from chapter 7. So again, they must follow the two requirements here, bigger than 10. We already did above. Now let's construct the confidence interval. So make sure that you take 1 minus alpha and multiply that by 100%. That is the confidence interval for P1 minus P2, and then given by the bound here. So we take P hat, which we found above, right? P hat plus or minus the margin error. This is the stuff from chapter 7. Or P hat is just P1 minus P2, P1 hat minus P2 hat, plus or minus z of alpha over 2 multiplied by the whole thing, the whole formula here. So the upper bound should be the plus side, and the lower bound should be the minus side. So just memorize the formula, and you should be able to do that. Okay, let's try the next example. So this one, we pretty much use the same example from last time. I mean last page. So again, that's economists. They want to compare, right, the internet access between the urban households and the rural households. We have the same data, 800 and 338. Same thing. Now we want to construct 99% confidence interval for the difference between the proportion. Remember, originally P1 equal P2, the nose hypothesis. Now we want the 99% confidence interval for the difference between the two, right? So we want to compare that. So we have already verified the requirements from the last example. So that's good. Now let's do the testing. So from the previous example, we already found P1 hat to be 0.4225, and we know that N1 is 800. P2 hat is 0.3893, and 750. Now alpha is 1 minus 0.99. Because we are 99%, that means you take 1 subtract 0.99, which is 0.01. And alpha over 2, this divided by 2 gives you 0.005. And you are looking for the z of alpha over 2 in the formula. So this one is actually z of that 0.005. How do I find that? So recall from chapter 7, you are using the I and V inverse norm, right? And then you take 1 minus whatever you have here, or alpha over 2, which is 0.005. And using the TID 384, you should guess the z-score for alpha over 2 to be 2.58. Once you have that, you can find the bounds from the formula I just talked above. So P1 hat minus P2, right? And plus or minus z alpha over 2. That's why we have to find the z alpha over 2 here. And then multiply by P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. And again, this bounds I just apply directly from here, right? Nothing is new at this point. So z P1 is this, P2 is this, z alpha over 2 is this, right? We all have N1 and 2. So all the info are ready for you to plug in. And if you do the plus 1, the plus 1 is the so that 2, right? The upper bound and the lower bound. If you do the plus side first, you get the upper bound of 0.0974. If you do minus, then you get the lower to be minus 0.0311. Now remember, originally we said that we claim that P1 is greater than P2, right? That means if you move the P2 to the left side, you should get P1 minus P2 to be bigger than 0. From the last example, go back there. So we claim here, right here. So you can write this, and you can move the P2 to the left side and make sure P1 minus P2 is bigger than 0. So that's the key point here. Let's move down to this one. Okay, so once you obtain the confidence interval, you got that, right? Now how do we interpret the result here? We are 99% confident that the difference between the proportion of urban households have the internet access and the proportion of the rural households that have internet access is between between this one or minus 0.0311 and this one, the lower and the upper, 0.974. So we are 99% confident that the value should be between these two. However, because the confident intervals contain a zero, because we are going from negative to positive, so it's also contain a zero. So we are unable to conclude that the proportion of urban households with the internet access is bigger than the proportion of the rural households with the internet access. The reason that we are unable to make the to conclude that this is bigger than, because if you look at here, P1 minus P2 should be bigger than 0, right? Should be bigger than 0, and the 99% confident interval include the negative number. So that means this condition is not satisfied, or we are unable to conclude that it is greater than. Okay, so that's why you rewrite this as this one, so you can make the conclusion for the confident interval. So the difference should be bigger than 0, but we also include some negative number, so that's not good. We are unable to conclude the claim. So that is the end of the first section, and this is about the mean. About the proportion. And you can use the next page here for the instruction about the TI 8384, and we will start the next one in the next video.